Welcome to Time Series Lesson 9. We're going to introduce Fourier analysis, and there's a lot to learn about this, but we're going to start with the basic fundamentals so we can lay a good foundation. A lot of this first lesson about Fourier analysis may be stuff you already know, but maybe in a way that hasn't been presented before, and I want you to understand what's really going on, so stick with me. At the very end of this lesson, we'll get to something that you may not have seen before, and after this, we'll have several lessons on this, which will deal with a lot of stuff you haven't seen before, especially the Fourier analysis for data that is not evenly sampled in time. But I'm getting ahead of myself. Let's get down to brass tacks. Suppose you had some data. Maybe you had data for 2 different days, so that the first time was time 0, we'll call it. The second time was time 1, and the data values are 27.3 and 28.4. Well, one way to represent the data is just give the data values. But there's another way. We could represent it as a linear function of time. We could say that x equals 27.3 plus 1.1 times time. Now, this function is defined only on a very limited time domain, namely times 0 and 1. I can graph this function, which I've done here. I've graphed it as a straight line with 2 data points representing the actual data. Notice that I plotted it for times in between the observed times and before and after the observed times. That's just for convenience, so you can see the straight line. It doesn't actually exist for those times. That straight line I've graphed here is just for convenient visualization. Okay, let's suppose, by the way, the new way is a representative of the data with some basis functions. The first basis function, which I've called psi sub 0, is the unit function. It's equal to 1 at all times. The second basis function, which I've called psi 1, is the time function. It's equal to the time for all times. And that way we were able to represent our data as a combination of basis functions. Well, suppose we take a third data point at the third day, which is time 2. Now we have data values 27.3, 28.4, and 27.7. Well, we can still represent it with basis functions, but we have 3 data points, so we need 3 basis functions. Let's use the power of 2 times squared. Well, then our data can be written as 27.3 plus 2 times time minus 0.9 times time squared. And notice that this is the sum of a set of coefficients, C0, C1, and C2, times basis functions, psi0, psi1, and psi2. And do bear in mind, this function is only defined on a very limited time domain, mainly the times being 0, 1, and 2. I can graph this function too, and once again, I've graphed it for times in between the observations and before and after the observations. But that's just for convenient visualization. The function doesn't actually exist at times other than 0, 1, and 2. Well, when we're representing data in general, we can represent any n data values as a polynomial of degree n minus 1, because that polynomial has n degrees of freedom. For example, if we had 9 data values, we'd need an 8th degree polynomial like this. And I could even take 9 data values, compute the right 8th degree polynomial, and plot it. Once again, I've plotted it for times in between the observations and before and after the observations, but that's just for convenience to give you an idea what the polynomial looks like. It's only our function to represent our data is only defined and only exists at the times of observation. Well, we're representing data by 9 basis functions, and we're using powers of time from the power 0, which is the unit function, all the way up to the power 8, t to the 8th power. And again, we have our function defined as a sum of coefficients times basis functions, defined only on the limited time domain, the times of observation. Well, giving the data values instead of some polynomial in time, it's also a basis function representation. If we define basis functions in the following way, I've called them delta functions. Delta sub j of time is equal to 1 if the time is equal to j, and equal to 0 otherwise. And then we can express it as a function, which is a sum of coefficients times basis functions, and the coefficients turn out to be the data values themselves, which makes the delta basis rather convenient. Any n data values will define a point in an n-dimensional space. In fact, we can treat that as a vector space if we want, which we often do. I tend to call it sampling space, and we can define it simply by using the data values as its coordinates. But, and this is a big but, that space, sampling space, it exists quite apart from any choice of coordinate system, because using the delta functions, that corresponds to choosing a coordinate system. We can use any suitable coordinate system, which means we can select any suitable set of basis vectors or basis functions. We can always represent the point as a sum of constants times basis functions. The delta basis can be called the canonical basis because in a way it's kind of the most natural, and the coefficients that we need turn out to be the data values themselves. But it's hardly the only one. Powers of time also make a perfectly good basis, in which case our function turns out to be a polynomial in time. What makes a basis set a good one, an acceptable one? To have an acceptable basis, the basis functions have to span the space. That means that any point in the space can be represented as a sum of coefficients times basis functions. And to do that, we're going to need at least as many basis functions as we have data values. But we also need to avoid redundancy, so in fact we need exactly as many basis functions as we have data values. Also, they have to be, even if we have exactly the same number of basis functions as we have data values, we still have to avoid redundancy in our basis functions. This means that the only way to get the 0 point, or the 0 vector, is to have all the expansion coefficients equal to 0. In other words, if the sum of coefficients times basis functions is equal to 0 for all times in our domain, that is the times of observation, that requires that the coefficients have to all be 0. This is the definition of the trial functions, trial vectors, being linearly independent. So, to have a good basis set, we have to have as many basis functions as we have data points, and all the basis functions have to be linearly independent.